He's like in his 60s and no one wants to learn that. There's no job. So exactly. He's just like working a few hours remotely to like nobody knows how to do it. It is pretty silly. Like I was watching this talk about how in healthcare up until like 14 years ago or so, like 80% of hospitals ran on paper. So much of that is just brand new. It's all this is designed for the internet system. So I remember like I was drawn a lot in that
Hey Aaron, can you hear us okay? Can you say something, Robert?
Hey.
Can you guys hear Robert okay? Can you do a test? Like maybe sing something or
Testing, 1, 2, 3. Testing, 1, 2,
Great.
3.
Okay, let's see what they say.
Yeah.
There's a bit of a delay.
A delay. Well, slight delay.
Okay, awesome. Cool. So here we are. This is below sea level. It's our 4th meetup. Just to really quickly reiterate what this is about, this is just an attempt to get people who are interested in systems programming together in New Orleans. We stream this on Twitch and we record the talks. It's very loosely kind of systems programming related, so if you have anything that you're kind of interested in, you might be able to talk on, let us know. The next couple talks coming up, we have one in mid-July. Usually it's the first Tuesday of the month. We're going to do it in mid-July because on the 3rd Tuesday because of July 4th, and we're going to be out of town. And that'll be Neil Mock. And then we're going to have another talk again on August 1st. And then after that, the schedule's open. So if there's anyone who has an idea for a talk, or if you don't have an idea for a talk and you want to do a talk, come talk to us. You can reach out to me or Aaron Lee, who is also one of the co-organizers on this event, and he's at home today. Yeah, and this event is sponsored by Dalipso. So we sponsor the pizza and the space. So check us out. We're always hiring. And come talk to us or talk to me if you're interested in a job or you're interested in anything working on systems programming full time. So let's get started. So today we have Robert Ismo. Did I say your last name right?
Yeah.
We have Robert Ismo, who's been kind of my guide into a lot of AI stuff. He's been really helpful to me. And he's going to be talking about some stuff that he's been doing, a company that he started, and the work he's been doing with semantic search. So why don't I just hand it over to you, Robert? Get started.
Hey everyone, so I'm Robert, and I have a company called Sifly, and we do a lot of work with semantic warehousing. So today I wanted to kind of give a little slice of some of the things that we have going on with semantic search. And so I think we can start off with what is the problem here. So we have a lot of documents, right? And we want to retrieve what relevant documents to whatever query we have, right? And so that's kind of a big problem space, right? So that's something like Google, for example, that's a big thing for them, or Facebook, or Twitter, or any kind of company with large amounts of data, and they need to find a way, how can we take a query and find what is actually relevant there, And so that's kind of a big problem. And so the first thing I want to kind of say is that I want this kind of to be slightly interactive, right, in a sense. So we're going to do a lot of searching here, and so with that searching, if you have any queries that you'd like to do and see go on as we go about this, then definitely let me know. So what's kind of the start of this? What's kind of going to be the overall environment that we're going to be working in? So we have 1,000 random Wikipedia articles and their first 3 sentences. So we have the title of the article, and we have 1,000 3 sentences worth of words, They're new line separated. There are no special characters. They're all lowercase, no double spacing or any other type of white spacing. They're completely normalized, something really easy to work with, so that we can mainly focus on kind of the ideas rather than necessarily, the data part of this. And so here, what we can do here, I'm going to show a little bit of what we've got going on. So here is the document that we have going on here, right? So we start off with like a title, and then after the title, we have, the actual sentences from the article, right? Right. And so there are a good 1,000 of them, so there should be 2,000 lines. Yep, and there are 2,000 lines, great. So, what we want to do is we want to build a way. How can we, given some type of idea, some intent, how can we search through these 1,000 documents and get what we're really looking for? So, I think the first thing that we should do is just kind of get into a little bit of understanding about kind of what we're doing here. So we're going to go and make this real quick. Cool. And here, let me actually make the text slightly, maybe not that big, slightly bigger for you guys. Yes. And so we are going to start off with our intro 1. So intro 1, just going to have a little thing for you guys, and it's going to give us the first document's title, right? So first document, Wolf Laurel, North Carolina. Great, great, great. We have an intro 2 for us. And what intro 2 is going to do is, intro 2 is going to give us the link to the Wikipedia article, because that's going to be kind of a big part of this. Is once we have an article, how do we actually tell whether it actually makes sense or it means something to us, right? So let's go and see what this is. This is Wolf Laurel, North Carolina. It's an unincorporated private gated community located in Madison and Yankee counties of western North Carolina. Great. Okay. So now we have intro 3. So this will kind of show the last bit of this. In intro 3, we'll just pull some titles and descriptions from the random, document kind of list there, so that we can say like, okay, we can pull in the actual document, we can pull in the titles. Great. Once we kind of have this boilerplate, we can start working with it a little bit more, right? And so here's that code right there, right? Let's actually get into some search, right? So we're not actually going to start off with semantic search, right? So first thing we're going to do is like, how can we actually search a document, right? And so the first thing here is that we have this little boilerplate here. And so let me get it started so that we can actually work with this. So it's going to ask for a search query. What is this actually doing? So what it's going to do is it's going to initialize a results object or a results struct that we can actually have all these results and have kind of the score that we give to them, right? We're going to pull in some string from kind of our input, so whatever we kind of type here, we can pull that in fairly simply. And here, let me full screen this just to make it even easier to see. There we go. And so after that, we're going to do a single term search, right? So this is, I think, the simplest form of search that we can do, right? If given a query, right, can we search if that document contains that query, right? So let's do something fairly simple, like someone give me a query that we can ask, a single term, anything.
Barbecue.
Barbecue. So let's do barbecue. How do you spell barbecue? B-R-B-E-Q-E.
I don't know.
Is that?
Sounds right.
Oh wait, let me get rid of that F. Wait. Oh. Let's go and barbecue. Is that?
I mean, this will be in North Carolina, right? So I assume
Yeah,
there's got to be some document, something.
We're gonna
do
do barbecue, and as you see, we got 0 on the scores. So it had no idea what we were talking about when we said barbecue. Why? Because this is a pretty bad search, right? Let's think of something different, right? So first, we see right here that we have this wolf here, right? So let's search for wolf.
Wait, I have a question.
Oh, go for it.
Why you say that it's a bad search?
So, actually, here, we'll get into that, right? So let's do wolf. Let's do wolf. Let's see what wolf gives us. So wolf will give us 5 queries, right? So we see Wolf Laurel. That makes sense why we got that. That's pretty good, right? Then we have a list of award-winning graphic novels. Why wolf has anything to do with award-winning graphic novels? Who knows? Then we go down a little bit more, and then we see Trinchia wolfi. What Trinchia wolfi is, I don't know, but it has wolf in it, right? And so, to answer your question, why is this a bad search? What this kind of single-term search is doing is it's basically saying, okay, you have this term. Does the document contain this term? And that's it, right? So if none of our 1,000 articles say barbecue, then we're not going to get any good search back. We're getting actually nothing back, right? And so for this, with our wolf here, right, we have 5 things that say wolf. So let's actually look at one of them. Let's look at the list of award-winning graphic novels, right? So let's click on this, and let's search for wolf, right? And you see, it does in fact contain the word wolf, right? So maybe that's why it actually came up, right? Yes. And so to go a little bit deeper into what this is doing, so once it has this kind of results, once it has these results, what is single-term search doing? Well, single-term search, let's go through it. A single-term search is going to take in the document. It's going to take in this results, and it's going to take in our term. It's going to go through every single, document in our results, right? It's going to get the content of the document, and then it's going to say, is memory contained? Literally what this is doing is it's checking, is wolf, like the binary data of wolf, contained inside of the entire binary data of the document? This is really bad search, right? Like this is, if there's any type of, discrepancies, like let's say there's a capital letter, like you do, for example, you do wolf capital, then we get a 0 all the way through because it is doing a pure binary comparison. So this is pretty bad. How can we improve this? Well, let's go into some multi-search, right? Because another big issue is, let's say we do wolf.
There is a
So
capital.
you're telling me with all those names that it wasn't uppercase?
So we lowercased all the documents before we put them in, just to normalize all of them. Yes, yeah. So we lowercase all the documents just to make sure, like here, yeah. So we have new line separated, no special characters, so there's no comma, exclamation point, anything like that. They're all lowercase. There's no double spacing. It's a fairly normalized document, just so we can work with it.
Linear search, right?
Yeah, it's literally just a linear search, right? And so now let's try to see where this kind of has an issue. So we know that wolf is inside the, let's search wolf again. So we know that we have this list of award-winning graphic novels. That's pretty cool. So if we do wolf graphic, right? That should show up, right? Because it's wolf and it's graphic novels. This should show up. But it doesn't. Why? Because this only searches for one term, right? And so if it does not see the term wolf graphic inside of the document, it's not going to return anything back to us. So that's pretty bad. So now, let's go and get out of that. Let's improve upon this a little bit more. So let's do multi-term search. So it's going to do exactly what single-term search did, but instead we're going to use this multi-function here. And so what does multi do, right? So multi is going to do basically a similar thing. It's going to go through every single document. And after it goes to the document, it's going to split up the terms. Well, actually, we do the splitting here. So we're going to split up the terms here, by spaces. And then after it's split up the terms, then it's going to do that exact same, is this contained, right? And then it's going to add it to the scores, right? Instead of just setting it to the scores. So what this allows us to do is it allows us to have multiple terms set up. So if we do, for example, wolf graphic, then a list of award-winning graphic novels gives us a 2. Great. Now, give me another search. You had a question?
Oh, no.
Oh, okay, sorry, yeah. What's another search you guys have? What else would you like to look into besides wolves and graphic novels?
County.
Counties. Let's go and say county. So if we do county, then we get K. Kimball, I can't, I'm not gonna try. Lake Shaffey, G. Edward Doer Jr., and all of the rest of this, right? So when you do county, you get a pretty good amount. So let's go into county K, right? What has county and K? So there's nothing else with county and K. Let's do county and let's say United States. There we go. County and United States. We get Franklin Grove Township, Lee County, Illinois. Let's click on this and see a little bit about this. So formerly China Township, it's one of the two in Lee County, USA. Boom, change from town to cool. We searched something. So this is a much better search than just single term, right? But it's also still pretty bad because we still have quite a few issues with this. But we can improve it slightly, right? So how many of you use Google? Wow. Okay, great. So how many of you use search operators in Google? Great. Who does not know what a search operator is? Okay, great. So a search operator, right? That's one way that we can improve upon this and make this slightly better, right? So we have search 3, and what search 3 does the exact same thing, but it does multi-search with operators. And what does multi-search with operators do? Multi-search with operators, it's going to go through and it's going to have this penalty, right? So this penalty is going to be 0 at first because there's no issue, right? As we go through each term, it's then going to go and see, is the memory contained if there's a plus? If the memory contained and there's a plus, good, don't do anything, right? If the memory is contained and there's not a plus, then you're going to set the penalty to the minimum int, which is like this massively small number. Or not massively small, but this large negative number to basically penalize this result, right? If we want it to contain something, but it doesn't contain it, then we're going to penalize the result, right? If we have the minus operator, right, then if it does contain that term, then we're going to penalize that result, right? So we're going to have this int min penalty as well, right? And if it doesn't, then we're just going to do the regular score, right? And then if there's no search operator, then we're just going to do exactly what we were doing before, right? And so let's go. Well, what's a regular query that you guys would like to do? I feel like you have one, man. You right there? Yeah.
Oh, just tomato.
Tomato. Okay, tomato. Got you. Is that how you spell tomato? I'm gonna assume it is. There is that we have nothing in tomato. These were 1,000 random articles, so.
It's a shame.
Yeah. Give another one.
Tequila.
Tequila. Let's see if we have anything with tequila in it. No tequila either. That. We shoot twice and we miss. Transportation. Okay, we have 3 things with transportation. We have the Okayama Electric Tramway, Kalik Energy, and People Mover. Cool. So let's look into these a little bit more, right? So let's look at People Mover, right? People Mover in Venice is an automated elevated shuttle train which connects the Pizzal Roma, the major transportation hub of the city, and the Trocadero Island with a car parking facility. Cool. This is not what we care about. So let's go and try to remove this from what we're doing. So let's go and do transportation once again. Transportation, right? And let's take out, what should we take out? To get rid of People Mover, but keep everything else. What's something that's unique about people?
Maybe Venice or something.
Venice, right? So let's take out Venice, right? So if we take out Venice, then we have no more People Mover, right? All we have is Kalik Energy and Okayama Electric Tramway, great? And we can also do something in reverse. Let's say we want to make sure that our result has, let's look at Okayama Electric Tramway, right? Or let's look at Kalik Energy. Kalik Energy is Turkish energy company of the Kalik Holding. Let's make sure that we're only getting things from Turkey because we're from Turkey. We're not actually from Turkey, but we're just gonna say that for now. So we only want things from Turkey. So we're gonna get rid of things from Venice because why do we care about Venice? And let's add Turkey here. And now Kalik Energy becomes number 1. Right? So we have, in a sense, a form of search here. It's still pretty bad. Why is this pretty bad? So let's go to our little notes here. Actually, I have a little example for us. Who is the best painter in the world? You might ask this on Google. So let's ask our little search engine. What is this? What is the answer to this? Right? Who is the best? Oh,
Dali.
say it again.
Dali.
Oh yeah, Dali. I don't know if we have Dali in here, but let's check. Who is the best painter in the world?
We have the Barcelona guy here.
So, guys, the best painter in the world is Anamari Kekara.
That's
surprising.
Guess who do you think Anamari Kikara is? Any guesses who you think this is? No idea. No idea. Well, let's go and click on Anamari Kikara. Anamari Kikara is a Finnish long distance runner. Her best achievement in track is running 9th place in the 1995 World Championship in the 1,000 meters and the 10,000 meters. We got it.
Great painter.
Yeah, and so this is pretty bad. What went wrong here? What went wrong here? So she's not a painter, and she's not necessarily best in the world at what she does. She's pretty good though. So let's look at what the issue is here.
Can you explain a little bit the score? Because I see that it keeps increasing, but I'm not sure that I'm following.
So the score is basically, the score is just what we use to sort the results. So in our search, right, we have multi-term search. Basically, the score gets increased if you have the operator that we're looking for. If we say like we want this operator and you have it, we're going to increase the score. If we say we don't want this term and you don't have it, then we're going to increase the score. And if we don't have any special operator and you have the term, then we're going to increase the score. Score is just what we use to actually do the sorting. So if we have this little function sort by scores, and it's going to take these scores and it's going to do that sorting with these scores here. And these scores are going to be in a little bit more as we go on to the next thing. Once these scores kind of have a little bit more meaning to them.
So you're taking your sentence with multiple words, parsing it out by the spaces, coming up with your multiple terms, adding in your operands based on what you've got, and then you're running an in search with those words per file, right?
Basically,
and
yes.
then the results that come back that match for each word or that's in the multi-part, it gets added to that score.
Yes.
So if you asked a question with 5 terms and it found a document with 4, you would get in elementary terms, you get a 4.
You would get a 4 for a score, exactly.
And that's what we're doing here. So we're right now at N.
Mm-hmm.
We're an order of N right now.
Yes, exactly. And so, if we look at who is the best painter in the world, we got a score of 6, right? Let's look at Katrina Miller. Is Katrina Miller a painter? No, Katrina Miller is a Olympic skier. That's not helpful either. Let's look at maybe the FP45 Liberator. I don't know about that one. Alexander, let's see, is he a painter? No, he's also an athlete. Let's see, are any of these painters? Let's go down to, let's say, the Daryl Goodrich. He was a director, okay, so he's got some type of, artistic ability in him. He's not an athlete, so that's kind of okay. But what went wrong here? Well, what went wrong was that, let's look at who is the best painter in the world. And let's look at Anamari. World is the,
She is the
So
best.
it scored high because it had those words.
yes, only
Mine
because
is painter.
best, and she doesn't have painter. And so if we look at this, she has, and then let's see if we have a who here. She doesn't have who either, but we have is, we have the, we have best, we have in, and we have the, and we have world, right? So that's 6 right there, That's kind of an issue. So, what is the problem here? Well, the problem here is that it is literally a direct memory check. So we can't do anything with uppercase. It's pretty bad in that sense, right? Because things are uppercase, lowercase. We can always kind of like lowercase things down, but also what about special characters as well that are kind of similar? Like, for example, Uber, right? If we type in Uber into, some type of search, Uber, word, let's say German word, Uber, it has this little, U above it, right? I forget what the name of this,
Umlaut.
Umlaut. Yes, there we go. We couldn't really check that because we're using a direct memory search. So if we have a U, good luck, We have no stop words, right? So we're giving things scores because they have a, the, of, is, these things are not important to the query. They add no value, and most sentences, most terms will have these anyway. So because of this, that's how we kind of got, Anna Maria as our top result, even though there's no reason why she really should be the top result at all, There's no conjunction. We have the word painter, but what about paint? We're checking for the term painter exactly. So if they have like, oh, I used to paint quite a bit in my childhood, we're not getting that result at all, you know? So that's kind of a problem. Lastly but not least, you know, we have no similar words. So without any similar words, what if I said he lost his watch, or he could not find his watch? You know, those two things are fairly similar in a sense, and that's kind of a hard thing to really understand the intent there, especially within the document and the query. What are you truly trying to get there? So we have a few solutions there on the side. So we could do like some string comparison instead of traditional, just like memory comparison to fix this. We could add a stop list to get rid of all of these like kind of unnecessary terms. We could add a conjugation dictionary. So like whenever we get a term, and if it's in our dictionary, get every single conjugation and add that to the terms as well. Or we could add a thesaurus. So we could start doing some weighting with like similar words to try to see if we can do something there. And then we have a kind of a bonus issue here. We have a wacky data set, you know, so we've got 1,000 random Wikipedia articles, so they're kind of all over the place on what they talk about. Traditionally, you're probably gonna have a lot more dense of a data set, or a data set that makes a lot more sense in comparison to each other. But this one's just kind of, you know, a fun thing with just kind of what we're doing right now. So let's look at this old kind of prompt that we had. Who is the best painter in the world? How would we make this to actually kind of make a better query for what we're working with our limited resources here? Best paint art world, right? So we want best because best is just a good word. We want to find best, right? Paint, because we can't do painter, because what if they just say paint, you know? Art, because that's a synonym to paint, you know, that's pretty good. And then world, because we want to make sure that they're the best in the world, you know? So that's going to be our big thing here. And so if we try this one now.
Now, would you want to add in who versus a what? Because you could cut with that, you could
Yeah.
get the actual painting versus the painter. So would you want to add who or what?
Yeah, that's actually an interesting one there. So the reason why I didn't add who is mainly because of the data set, right? So kind of going back to the wacky data set. So we have Wikipedia and we're only getting the first 3 sentences. The chances of a Wikipedia article having who in the first 3 sentences is very low. Because if you think about this, how Wikipedia articles tend to be introduced, if we go back to Safari, you know, it says that she is a, you know, former Finnish long distance runner. They are, you know, XYZ. You know, it's very, you know, definitive in how they speak about these people. And so you're probably not going to find many who's inside of kind of the first
So
term.
even though your random data set or your data set's random, you do have some pre-knowledge of
Yes, yes. And that's kind of the important thing here, is that that's kind of why I put this as a bonus thing, because your data set means quite a bit when you're doing search, you know. If you have some type of search, your data set means a lot. And so let's try and see what happens when we do best painter art world. When we do best painter art world, the first result is Painted Desert Project. That's pretty cool. What is Painted Desert Project? Is this like a band that makes like Skittles? Who knows? Painted Desert Art Project initiative which connects artists with communities through mural opportunities in the Navajo Nation. Okay, that is something to do with world, paint, art. You know, there's a connection there. Let's see. Let's look into it a little bit more. Oops. There we go. So let's see if we have paint. Well, of course, we have paint there. Let's see, best. There's no best. World. There is Thomas invited several world-renowned street artists, right? So we're getting world-renowned street artists. That's pretty nice. And then art, right? And so we have public art initiative. That's kind of the first term there. So that's pretty good, right? And one of the things you might have seen is that, let's look at article right here. You see how when I did Control F and it got article right here? The same issue would actually happen with our search that we're doing currently, is that if something kind of had the term in there, but it's not actually that term, we're also getting an issue there. So these are all pretty bad search, algorithms here, you know? These are all pretty bad search algorithms here, right? And none of these would be considered semantic search, right? And so what is semantic search, right? Semantic search is really about beyond just these queries, because really what we do is we have this query machine. That's what we're doing right now, right? But we want to go a little bit beyond that, right? So how do we understand the searcher's intent? And that's what semantic search is all about, is that if we have kind of an understanding about what they mean to say or what they mean to be looking for, then we can improve the search quite a bit more, right? So right now, there's kind of a lot of heavy lifting on you as the searcher to try to find these articles, right? But that really shouldn't be the case. Really, it should be more about, you know, kind of having similar ideas and then connecting these similar ideas and getting them, you know, close enough that, you know, we could get some pretty good search, right? We don't go on Google and we try to, you know, find every single word that could possibly be in the search and all the conjugations. Like, that's just not reasonable, right? And even if we did implement, let's say, all kind of 5 of these, right, or really 4, right? So we had string comparison, we added a stop list, we had a dictionary and a thesaurus to make sure that this search is a little bit better. It's still not going to beat, you know, really high quality semantic search. But how do we do semantic search, right? So that's going to be the next question. So semantic search, let me introduce you to this. The reason why I want to kind of go over this slightly bit, this is a transformer, is because I don't know if we're going to have a below sea level on transformers. So kind of making sure that everyone's up to speed on kind of how this works and why this is kind of a really great thing and how it kind of powers the modern internet, right? So behind, for example, like Google, or if you use ChatGPT or GPT, is this model right here, right? And so really what we want to care about is this side right here, not necessarily this decoder. So this side on the left is called our encoder, right? And so what it's going to do is we're going to have an input sequence, right? So we're going to have an input sequence like who is the best painter in the world, right? And it's going to have that input sequence. It's going to tokenize this input sequence. What does tokenize mean, right? We don't want to go just by words, right? So if we go just by words and say who is the best painter in the world, we're going to have a massive kind of set of things to deal with. Think about it. How many words are in the English language? Does anyone have a good guess how many words are in the English language?
Hundreds of thousands?
Probably quite a bit. I think it's actually in 60, 65 or something like that, 66, 65, right? And then you have to think about all the words that are not in the English language, right? So when you think about that, it becomes very hard to try to break things up by words, right? Because then you have to deal with what is the meaning of every single word, right? So what we do is we break it down by tokens, right? We can also break it down by characters, right? But that's really intensive if we broke it down by like every single character, like who, W-H-O space, I-S space. You know, like that's pretty intensive to go by every single character. So we break it up into these small token-like chunks. So let me give an example, right? So if we have who is the best painter in the world, who is the best painter in the world, right? We might break this down by who is, because these are very common, the best. These might be very common. But then once we get to painter, let's say we go pain, because that's a fairly common kind of string of, you know, tokens that we tend to get. And then ter, because ter is also common, in, the, and then let's say we have WRO, so were, and then LD, because a lot of things end in like an LD type of, like if you have like worldly, you know, like that's another one that kind of has an LD in it, right? So this might be a potential way that we can tokenize this. With these tokens, there are a lot fewer tokens that exist than there are words that exist, right? Because we're breaking them together by their commonality to make sure of this. And so what it does is once we have these tokens, right, we're going to do another step. Don't worry about positional embedding just yet. But then we're going to have this kind of multi-headed attention. What this does is this is going to take our kind of tokens that we've converted into vectors, and it's going to try to understand features about these, right? So if we have who is the best painter in the world, right? If we have this, right, it wants to try to understand some features, right? So maybe when it sees the feature who is the best, right, it's going to encode, let's go to the next kind of level here. It might start trying to look at and find who is the best. So find best, right? It might encode in a sense, find best. Find best what? Pain? Find best pain? I don't know about that one, you know, unless you're kind of a masochist or something. But let's go to the next token, painter, right? So it can kind of look into that and see like, oh, we're looking for a find best painter. Then we have a little bit more in what? In what? Were? What's a were? That means nothing. LD, it sees LD, so let's go world, right? So it might try to kind of break this down into meanings, right? So find best painter in world, right? So we go from who is the best painter in the world, right, to kind of these token representations to this kind of meaning representation. And so we would consider this kind of a semantic representation here. So we want to find the best painter in the world. Once it's done that, it's going to do a little bit more to actually kind of do a little bit more transformations here, just to kind of help the neural network kind of learn these features and things like that. So we don't have to worry necessarily a bit about that. What it's actually going to get into, what makes this really kind of interesting, is that it's going to kind of do this, like it's going to make this kind of semantic representation for every single token, right? So whenever we see the term who, it's going to have its own representation of what does who mean, right? What would who mean in the possible context of any place that you could use who? Who probably means that you have a question, right? So who means that you probably have like a question, right? So a question about a person, or we could say that who means that you probably have a question about a person, right? We can wrap this in quotation marks to really mean that this is like some semantic meaning. Is probably isn't that important, but you know that this probably is some type of, you know, subject to verb object. You're probably like placing something in. It's probably not that important though to the grander scheme of semantics. It's just something that all syntaxes tend to have. Same with the, right? So the, we're going to do the exact same thing. Best, right? If we see the term best, what it's going to do is it might make another vector, another kind of semantic vector there, and it might find most or best. Let's just say top, best. Kind of whatever kind of phrase you want to use, whatever idea we want to apply to the concept of best, it's going to kind of encode that as well. And then painter, right? If we get pain and then ter, right? So let's kind of combine these because it's probably not going to understand much about pain, but it might look for other embeddings that are going to kind of fill this in, right? And so as we kind of go into this and go kind of vector by vector by vector, it gets pretty complex, right? Because this is kind of the black box. Have any of you heard of kind of the black box idea of like a machine learning algorithm? Yeah, so that's kind of the idea here, is that we could try to break this up like token by token and understand how it's looking at these tokens and looking for things. But that's something that, you know, is a fairly open problem within like machine learning, because it's fairly hard to understand how do we even conceive, you know, who is the best painter.
Do you mean like the Chinese room theory? Is that what you're saying?
Yeah, actually, yeah, exactly that. Kind of in a sense, yeah. So you don't know how exactly they're getting to that answer, but they're getting to it somehow, you know? Because we have a fairly bad understanding of how we even get to the answers. Like what kind of even made us decide to get up here today, you know? So that's not something that we have a fairly clear understanding of, because semantics and understanding the meaning behind things is a fairly difficult task, right? So once we have this, and we have kind of these embeddings of what this vector is looking for, and it's going to do this multiple times depending on what model is or what model we're using, but we're not going to necessarily worry about that. But once we have these, we can then combine these together. We can combine all these kind of semantic meaning vectors together. Let's say we like add them, right? So we can say v1 plus v2 plus v3, whatever, as we go, so on, right? And at the end, we're going to get an embedding vector. And so the embedding vector is mainly going to be the kind of way that we're going to compare these different terms, right? So let's actually look at this in practice. So let's move out of C land and let's move into some Python, right? So Python is kind of how we tend to do machine learning work. And so hopefully after we get through this, you can kind of have a practical example of how you could possibly implement semantic search in your own kind of applications here. So we're going to start off, we're going to import transformers. We're going to import auto tokenizer and auto model from transformers. What is transformers? How many of you are familiar with Hugging Face? Great. So what transformers does is it allows you to kind of go through all of the Hugging Face models and pull them in, pull in their tokenizers, pull in their models, everything like that. We're going to implement torch. Torch is PyTorch. It's a machine learning library. We're going to implement FIAS. This is the Facebook AI semantic search library. What it does is it allows you to compare different vectors, these embedding vectors that we were working with before. It allows you to compare them in a way that's a little bit easier than doing like the linear algebra yourself. Right? Next, we're going to get NumPy. NumPy is just a math library. We're going to need that. And the rest is kind of just like some other stuff that we're going to add in just to make things a little bit easier for ourselves. Right? We're going to ignore this right here for a second. What we're going to do first is we have this model here, right? So we have to choose what model are we going to use. There are a lot of models. What I would actually kind of recommend is we have the embedding, hugging, face leaderboard. Let me see if I can find this leaderboard. There it is, yes. So this is kind of a leaderboard that Hugging Face puts on for embedding models and how good they are. It's not loading for a second. That's kind of unfortunate. But yeah, if you go to Hugging Face spaces MTEB, oh, there it is. Okay, great. Slash leaderboard. This is going to be a kind of repository of a bunch of different models that you could put into your own applications that do a variety of different embedding tasks, right? It's going to take a while to load, I guess. So, oh, wait, there it is, right. So here are all of them, right? So we have E5, large V2, instructor, E5 again, right? Yeah. So here's kind of a list of all of them. We have like 75 here. If you're familiar with OpenAI, we have Ada right here. Ada is number 6. That's kind of the embedding model that you can use whenever you use OpenAI's API. So it's pretty good. It does pretty decently, right? Today we're actually just going to use BERT, right? So BERT, base case, don't worry about necessarily the rest of this part, but really we're going to use BERT. And BERT is kind of one of the original kind of transformer models, right? Because we're really looking for something simple, and also my Mac probably could not handle if we use like instructor extra large, you know? So once we have that, we're going to pull out the tokenizer. As I said before, we need to tokenize this, but how do we define how we're going to tokenize this? We're just going to let someone else who's done this before kind of do this for us, because actually figuring out tokenization is kind of not really fun. So we're also going to pull out the model as well. And this is another big thing. If you ever want to implement something, look what other people have done for you, you know? So don't try to train a model from scratch. If we tried to do semantic search here in this live demo from scratch, we would be here all day, because it's probably going to take a couple hours just to train, and it's not even going to be that good, right? Let's go, and we're going to read the files, do all that, parse the files. We're going to build an index. Let's kind of skip over all of that, right? And so if we look at this here, I can actually run it for us. I'm going to do Python 3 search for .py, right? There we go. Okay. So it's going to start embedding for us while we wait. So it's going to, pull in the file. It's going to start tokenizing every single document that we have. And so how is it tokenizing? It's going to use the model.
Hey, could you make it a little bit bigger?
Oh, yeah, I got you. There we go. Is that good?
Yeah, I had to go one more bump if you could.
Thanks. There we go. Here, let me go and get rid of this here. And so now we have a model, and once we have the model, what we're going to do is we're going to pull in some hidden states. And so don't necessarily worry about this right now, but these hidden states, these last hidden states, are what we're going to use as our embedding, right? Once we have that, we're going to start pushing that to our kind of list of embeddings, and then we're going to save that just so we don't have to go through this whole embedding process again, because it's kind of long, because these models are pretty big and they take a while to run, especially
Can you explain again what it's doing, embedding the document?
Oh yeah. So what it's doing at the moment is it's taking every single document that we have, it's taking the content of that document, and it's running it through our model. What BERT does is BERT tries to complete things, right? BERT is a transformer that tries to complete text, right? So if I say the cat jumped, or the cow jumped over the moon, there you go, yeah, the cow jumped over, it's going to try to find moon, right? But instead of trying to do that completion, because we don't necessarily care about the completion, we're just going to take everything that it used to build that completion context, which are these last hidden states, and we're going to use that instead. And these last hidden states are actually going to be our embedding there. Once we have that, we're going to build an index. And once we have that, it's going to be exactly kind of the same idea that we had before. So once we have a built index, what are we going to do? We're going to have the index. We're going to stack everything up together, normalize it because we don't have to deal with these massive vectors, right? So we're going to normalize it. And then we're going to use phi-s to actually create these indexes. So there are a lot of different ways that we can compare vectors, right? So the easiest, most straightforward way is through an L2 norm, right? With an L2 norm, you're basically going and you're saying, what is, the Pythagorean theorem? So you're basically doing the Pythagorean theorem and you're finding how close are these things together, right? What is the closest thing to our query, right? The next one is the inner product, right? Inner product is what you tend to use for problems like this. The reason being is inner product doesn't necessarily care about the actual distance of things, right? What it cares about is what is the angle of things. So imagine we're on this massive circle, right? And this massive circle defines all meaning, right? And so let's say we have a point that's all the way up here, right? And we have a point that's right below it, right? And then we have a point that's slightly to the side, right? So our circle, it's kind of centered over here, and we've got these 3 points, right? With the L2 norm, these two are kind of closer, right? Just in space in general, in this metric space, right? But that's not necessarily very useful to us because these are, in a sense, conveying different meanings. You can think of this vector that's all the way up here as being just more intense, right? You can think of it as being more intense. But even though it's more intense, right, it's still conveying the same ideas, right? That's kind of a simplification, but that's kind of the idea of why we want to use inner product and compare angles rather than necessarily raw distances, right? Once we have that, actually, let me remove this because I actually didn't implement that. But let's look at these a little bit, right? So we have enter some search queries. What is a search query that we would like to try?
Is it the same data as before?
It's the same data, same data. Mm-hmm.
Who's the best painter in the world?
Say it again.
Who is the best painter in the world?
Yeah, who is the best painter in the world? Let's do that. So when we do that, we get Fadi Malouf. Who is Fadi Malouf? Is a German Lebanese pop and crossover opera singer. So they're not a painter, but they are an artist. I'll give it that. I'll give it that. So yeah, who's the best painter in the world? We got Fadi Malouf. Let's see. What about Hyman Schandler? Let's see. Who's this person? Violinist, teacher, conductor, who was co-founder of Conductor Cleveland Women's Orchestra. So also an artist, right? Let's look at the next one. List of public art in Queens. It's public art in Queens. Yeah, so that's pretty good. So what's another query? Anything that you want to search these 1,000 random Wikipedia documents for?
Fast cars.
Fast cars. Fast cars. Let's see. Okay, we do fast cars, and we get list of Ron Barron Investment Conference Entertainment. What is Ron Barron Investment Conference Entertainment? We've got Metropolitan Opera House, Bruno Mars. Do we have fast? Nope. Do we have cars?
Maybe Tracy Chapman played there.
Maybe, yeah. So, as you can see, there's some issues here. Why are there issues here? Well, the first major thing is that now we are using a model, right? And so this is the big thing about when you're doing these kind of semantic ideas, is that when you're using a model, is that there's a lot of, let's say, freedom that you're giving the model to understand these vectors, right? So the nice thing about who is the best painter in the world, it gave us a bunch of artists, right? Or it gave us pages about art. Right? So that's kind of semantically similar. Maybe in these 1,000 vectors, we don't have a single painter. I'll tell you that's wrong. There is a painter in here, but it just didn't find it. The major issue is that when you're dealing with a model, you have to make sure that these models can actually understand intent well, right? Because you're kind of trusting it. BERT base case is running on my small 8 gigabytes of memory MacBook. This is not a big model. It's actually very small. And so, because of this, we can actually look it up, see how small this is, right? So let's go to Hugging Face and see how big is this model. So, nope, that is not the model that we're looking for. Bert, there we go. I guess we can't. So yeah, this is the model that we're using here, and I always forget, how do you check the model size on Hugging Face? But beyond that, the important thing to realize is that this is a fairly small model, so it's probably not understanding fully exactly what we're looking for, right? So if we keep on searching, let's go and say dogs, right? If we search for dogs, we would hope we actually get list of Ron Barron Investment Conference Entertainment again, right? And one of the interesting things is that actually, if we look at this again, let's look at this again. Bruno Mars, right? Do you think that this vector, or not this vector, this model that we have was actually trained on the term Bruno Mars, or knows who Bruno Mars is? It might have had a few training examples that contained Bruno Mars at some point. Probably not. Miranda Lambert? Probably not. John Mulaney? Maybe, So that's kind of the big issue with this, is that if it doesn't know what you're saying, if you just had a random string of text, it's probably just going to be like, oh, that's reasonable, I guess,
Well, what if the semantic did ARS? You put in cars and Mars and...
Yeah, so if it has, let's say, cars, right? So let's go back to cars, right? Let's just search for cars. If you look at that, we have a list of highways numbered 214. That's a very interesting Wikipedia article. So it gives us Ron Barron again. But let's look at this again. List of automated train systems. Train cars exist. Let's see, does this actually have the term train cars in it? It doesn't have the term cars, but train and cars might be similar, right? And that's kind of the biggest issue with
It
this.
does.
Is that
It said self-driving car on the related topics.
Oh, it did? Where?
On the right in the little.
Oh.
On the bottom of that.
Oh, self-driving car. Oh, car. Gotcha. Yeah. So it does have car in it, right? And so with that, that's kind of probably where it's getting this from. And so that's kind of the big issue here, is that when you're doing these kind of semantic problems, is that it's a fairly difficult thing to understand. What is the intent here? And usually the best way of doing this, how do you improve this? We'll just use a bigger model, right? So at the moment for this, because we're kind of for time and not kind of waiting for this to go forever, we're kind of using a very small model here. But the idea here is fairly similar, is that we're going to create these vectors, right? And once we have these vectors, we're going to do some type of comparison, whether that be L2 norm, or we can also use cosine as well. This is actually really funny, because BERT actually doesn't do cosine norm very well at all, so these results are going to be horrible. So let's go and do that again. Here, let's do who is the best painter in the world. Boom. So when we do this, we actually get a list of Ron Barron Investment Conference Entertainment. We get Kirsch equations. We get beta amarin 24 hydroxylase. We get Clancluse, whatever that is. Basically, it has no idea what it's doing. Because BERT was not trained to actually be an embedding, this BERT model that we're using was not trained to be an embedding model for like text similarity. So whenever you try to use cosine similarity to actually figure out what's near each other, it actually does pretty horribly. So let's go back to L2 norm. Right? And the other big thing is that now we're not caring about the words at all. We're just completely trusting the vector. So when you actually look at something like Google, for example, how many of you have done something very similar to, you're searching for, let's say, how to cook an egg. You get, all these results, but you don't feel like, this isn't really what I'm looking for. So you may search and do something like YouTube, or you may do something like Reddit, or something like that, because you want to get results that are fairly similar to, like from this site, for example, right? Our model currently has no way of doing that, right? It purely tries to get semantic. So what is the semantic meaning of YouTube? Unless it was trained on the term YouTube, fairly well, then it has no idea what YouTube is. It might know what U is, it might know what a tube is, but YouTube together, it might have had a few examples with that, but overall, it's pretty lost, right? So really, how would we improve this even further? We would improve this even further by going and kind of taking the same ideas that we had from Search 3 of having these multi-term search with operators, right? And combining it with these semantic vectors. When we have this, we don't want to weight it fully on semantics, but also we don't want to weight it fully on just terms, right? We want to make sure that if we have terms, right, like if we have YouTube, that we're basically only searching for things in YouTube. And one of the ways that we can actually kind of make this even better is if we do like site, or let's do like Facebook, for example. Let's do like YouTube videos, right? If we do YouTube videos, and then say like Reddit or Facebook after. No, we actually do get video. We actually do get Facebook. But let's say like let's say YouTube videos, OpenAI.com. Boom. We don't get OpenAI.com, right? That's kind of lame, right? So what we can do here is we have a search operator where we can do site, and boom, now we only get things from OpenAI.com, right? So that's pretty cool, but we couldn't do that with just regular semantics. And so really the idea is that we want to kind of keep things together to where, or not together, but we want to kind of combine these two ideas. Search 3 is pretty cool because we can do all these search operators, we can find things that are exact matches, and we'll never necessarily have an issue with, you know, not finding something, like finding something that's completely irrelevant to the document, right? Unless we do like art and it finds like article of Confederation or something like that, and you're just like, oh, that's not what I was looking for. But with this, you know, we actually kind of get a little bit of meaning, right? So when we looked for painters, it gave us only artists, right? The first 3 results were artists, which is really good, right? That's something that you don't necessarily get. If we don't have the word painter in our search 3 with the multi-term, then it's just not going to find anything. It's just going to say 0 and just fail, right? So you want to kind of weight these both. And that weighting, where do you actually find that weighting, is really going to depend on the use case. And so I think that's kind of, I would say, a fairly small look into this idea of searching for things with semantics. And so, any questions?
I have a question. I feel that brought me to the past.
Yeah.
I remember like working on neural networks and things like that, and I always was having this problem that it seems like all the results, it seems accurate, but then they were like huge fuck ups, right?
Yeah.
And it's like how I weed these guys out.
Yeah.
Like other things like, or you know, like for sure that you can train the model, but you want the model not to train the model with the fucked up, right? Because it's like, okay, whatever is coming, it was the model to identify that and take it out. So how do you integrate this here? Like in what layer do you deal with that?
Yeah, so here we can actually give a pretty good example. Let's say we just do like some random, like, you know, just things here, just random text, right? And we search for this. Well, with that random text, apparently the most relevant thing is PS 114, which is probably like it's a province. Cool. That means absolutely nothing for us, you know? And so how do we actually deal with something like this? Let's say, for example, let's actually take exactly that same thing and let's put it into Google, right? Let's go and do, boom. When we search for this, Google's just gonna say, no, that means absolutely nothing, like, stop, you know? That's really where that kind of dual approach comes in, right? So we have these semantic vectors, which can help us quite a bit, but unless you have like a, you know, GPT-3 plus GPT-4 model that's like can just understand human language on a level that is somewhat beyond what search kind of needs, then you really kind of have to worry. You really kind of have to use more traditional algorithms here, or like, you know, filtering things out by if does it have these terms in it, right? So kind of going into what we had before, for a while, this is actually how Google worked. Google did the major like string comparison. It added like, it had the stop list. It was doing kind of conjugations, and it had a thesaurus. They were also doing slight vector work as well. But the major thing, kind of early Google, was mainly just these 4 things, because they're really important when you're doing a search, because it's not always just semantics, right? Sometimes it's about understanding like, hey, when I say I want, you know, Here, let me actually give a good example. Like when I say I want like a BMX bike, right? Well, maybe BMX might not be a good example, but let's say I wanted like, let's pretend like BMX was like a brand. Well, actually, I think BMX was originally a brand, but like if you wanted a BMX bike, you want to search for things with the term BMX in it. Not just like bikes and then like forget BMX, because I was never trained on that, you know? So I think especially when you're dealing with very small models that are not like foundational in a sense, having that type of filtering is really important, yeah. And like going into it, there are a lot of different methods of doing that, and I think really you should have the semantic step kind of at the start. And then beyond the start, then you start doing kind of that filtering to actually improve what you had going forward. Because in a sense, doing vector comparison is fairly fast for a machine because you can just put that on the GPU. But once you start getting into these like operators and all the kind of algorithms here, it's a fairly, not complex, but it requires a few more cycles to get going with that. And so usually you want to have a much smaller space that you're working with, and then from there kind of do the filtering. Yeah. Mm-hmm.
Sound right?
Yeah.
So I got a quick one. So a couple of times you mentioned the intent,
Yeah.
finding the intent. And intent is subjective to
Yeah.
the person, correct?
Mm-hmm.
So we kind of have to, this is a question, you kind of have to, I would assume, do your vector or do your semantics based on your intent. So are you having to retrain, or are you training your semantics toward a specific intent? So if each one of us had a different data set, but yet we know how we want to interact with that data set, that semantics has to be based on our intent.
Mm-hmm. Yeah, no, I completely feel you.
Like, it's not like one size fits all.
Yeah, definitely. And so what I'm actually going to do is I'm going to recommend to you all, anyone who actually wants to kind of implement some form of semantic search within like an application that they're doing at the moment, you know, any type of semantics or anything like that. Okay, we got you. Okay, great. So what I would recommend for something like this is there is this model right here, Instructor. Instructor is actually the model that I use in production for a lot of the work that I do, and it kind of answers your question there. Instructor is pretty cool. It's actually Instructor. There we go. Instructor is pretty cool for that exact reason. So BERT, for example, was trained to be a sentence completer. Just like a lot of these embedding models, they are trained to find what is the next token going to be. So they're not really made to be embedding models in a sense. And so Instructor, and by its kind of very good score on this leaderboard, just like embedding 5 large v2, these were made to be embedding models. So these kind of solve one of the first issues is how do you find intent? Well, if you have a model that's actually made to find intent rather than like a sentence completer that just kind of happens to find intent because it needs that to complete a sentence, then you're starting off on a way better footing, right? Instructor is really cool because you can actually give instructions to the model to tell it how you want to embed what you're currently doing. So let me see if they have their example here. Actually, yes, here it is. So you can say something like, represent the Amazon title for retrieving relevant reviews. That's pretty cool, right? You can represent the sentence for retrieving duplicate sentences. Represent the image caption for retrieving duplicate captions, right? So we can do stuff like that, which is pretty cool. So let's say that someone is talking about, they want to search Wikipedia, right? If you're searching Wikipedia, really what you want to do is you want to represent that search for retrieve relevant documents. But let's say someone is looking to, answer a question, right? They're on Quora, right? You all are familiar with Quora and stuff like that, or they're on Stack Overflow or Stack Exchange, right? You can represent the question to retrieve relevant answers as well. Like you can basically tell the model, it's basically kind of like 2 LLMs that kind of combine together at the end, to tell the model how exactly are you looking to represent this actual query so that you can find these other queries. And then you can also do the reverse as well. You can represent the caption, you can represent the statement, actually what was I looking for? Yeah, here it is. Represent the medical statement for retrieval. If you represent the medical statement for retrieval, someone else can go back and say, represent the medical question for retrieving medical statements. And boom, these 2 vectors will come together. So the vector that's caused from this one, that's an image, dang. no, that's not an image. Okay. The vector that's caused from represent the medical statement and represent the medical question for retrieving the medical statement will come together if they're talking about the same thing. And so it's one of those things where Instructor is a really cool model. I think if you're doing anything that has this like multi-intent kind of facet to it, in which there are multiple ways at which someone could look at something, this is a really good kind of technology to use there. But then going even further than that, that's kind of just a big open problem in, it's not even an open problem, it's just kind of the limitation, right? When all we have is text, right, then there are a lot of issues with how we're going to search or find out what the actual intent was just from text. Maybe if we were like recording your webcam, we had your microphone, we were seeing your text, we were looking at how long you're typing, we get every single data about you, we have like a blood pressure monitor on you. Then maybe we could get better intent about like what you actually meant. But the biggest thing is that how can we get this intent from like a text? You basically can only work with what you've got. And so I think this is a pretty good step towards that. Oh, yeah.
One quick one, like, is the way you're getting the embedding, so you're ending up with like a single vector for the query and a single vector for the Wikipedia?
Yeah.
By just taking the mean of all the embeddings per token?
Yeah.
Is that like the de facto?
Yeah, it tends to be. So that's mainly because it's a transformer. Transformers are kind of the major way that people tend to do language tasks or any sequence tasks in general. So really what it's doing is, let's say we have like a list of tokens. So we have like token A, we have token A, B, and C, right, that go into it. What we then want to do is we want to have like token A1, B1, and C1, where we're going to have vector A1, B1, and C1, which tries, when you look at the entire A, B, C, what is the meaning of A, what is the meaning of B, and what is the meaning of C? And then we could do that again. There's nothing stopping us from doing that again and going C2 and saying, based on A1, B1, and C1, what is the meaning of A1, right? So we can make another vector, and we keep on doing this over and over and over again until we finally like decide to end. Because one of the nice things is that we can, with this model, this kind of both of these sides, we can stack on top of each other as much as we wanted to keep on doing this over and over and over again. And eventually we're gonna get to like B final, and A final, B final, and C final, right? And then what it does is it does some type of, aggregation to bring these together. And usually that could be like a sum, right? So you sum these together, and once you have the sum, that's going to be our embedding vector. And the nice thing about this is that and the reason why BERT is kind of a bad model to use for embedding, but it's just a very small model, so it's very easy to work with. But the reason why you'd want to use these is that these were trained to actually do these embedding tasks on the summation, right? Because BERT was not trained to do an embedding task on the summation. It was trained to do like a softmax on the final, hidden layers, right? And so once you kind of have that, that's kind of the idea there, is that once you have these kind of meaning things, like you finally have the true meaning of A, the true meaning of B, true meaning of C, add these together, you get kind of the true meaning of the sentence. And it kind of depends on how you trained your model to go about that task.
Gotcha.
Yeah.
Okay, we're gonna have to shut it down, but you guys can feel free to talk to him. Are you going to go to Hack Night after?
Yeah.
Okay, so normally after this we walk down to Hack Night at the Rusty Nail, just a couple blocks away. Yeah, you can just take that elevator down, just walk down there or follow us or anything. But yeah, I just want to say thank you, Robert. Learned a lot. Can't wait to go home and try some of that stuff out. But yeah, see you guys later. Thanks for joining.